Hello, Kim. Welcome back. We're doing well. Hello, Jordan. Good morning. Welcome back. We're doing well. Thanks for emailing me about those examples. I just sent you one back. The warm-ups and the examples aren't going towards your grades still. Just want to let you know that we do them together, so they won't be graded. Exit passes will. Hey, Tristan. Welcome back. Good morning, John. Welcome back. Hey, Michael. Hello, Santino. Good morning, Kai. Welcome back. Hope you're doing well. No problem. Jordan. Irvin, welcome back. Good morning. Joey G. Good morning. Welcome back. Yeah, Seam. Good morning. Happy Monday, Faith. Good morning. Hi, Jumila. Hi, Joseph. Hey, Ellen. Welcome back. Happy Monday. Hi, Micaiah. Welcome back. Nadina. Hey, Tintin. Good morning, Wendy. Hey, Rye. Hopefully you had a good weekend. Welcome back. Hello, Emma. Welcome. Junior. Hi, Frank. Welcome back. Hi, Nadal. He's in. Welcome back. Hey, Philip. Good morning. Thanks, Joe, for letting me know. Joey G. Getting better at that day crescendo there. Welcome back. Happy Monday. Hopefully you guys are doing well. It's been a while since I've seen you guys. Thursday was our last class. Friday, you guys obviously had off from chem class. You had that nice cold weekend. Hopefully you guys are nice and warm. Cuddled up by maybe a heater or something, fire, and some chemistry, hopefully. All right, so here we go. Hopefully we're back or safe, healthy. Let's start off with the attendance. I'm looking for Alex, Greg. I'm looking for Leonardo, and Bellman just popped in. So Greg and Leonardo, if you're here, please let me know. Hi, Bellman. Good morning. You have a late pass, Bellman? I'm just kidding, Bellman. Feels weird to say that, doesn't it? Hey, Alex. Try to get here 2 minutes earlier. Bellman is what? Likewise. All right, so here we go. Let's check out the COVID update since the last time we were in class. So over the weekend, we accumulated more cases. No surprise, that number has been growing drastically, since the beginning of the school year. Been watching it daily. I think it's important. Maybe other classes are talking about it, maybe not. We have 6,249 cases of COVID in Oneida County. That stinks. We have, 178 people in the hospital system. That's a lot of people. I talked to my friend at the hospital. My friend's my sister-in-law. And she works at the hospital, so I talk to her often about like how's the hospital doing. And she said last week there's 3 days that they diverted ambulances to like Oneida Hospital or Rome Hospital or elsewhere. So that number should definitely be greater because there's a lot of people that wanted to go to the hospital, to go to our local hospital. Who wants to go to Oneida for some treatments? Not really. So that number should definitely be greater. Our hospital system is, I guess, more ready, available for more patients, but they're still overwhelmed. There are 26 people that are in ICU, and the number that really stinks for us is 266 people died from COVID. So yeah, that's 266 families. Maybe it's someone's grandparents, maybe someone's father, someone's spouse. So all those families have been impacted. Obviously, they get impacted by death, but now that pandemic has directly impacted them. The number that was really popped up to me yesterday was this one right here. The number of daily deaths, deceased. So on the last day that we had data, the 9th, they recorded 8 deaths in one 24-hour span. So 8 people died from COVID in one day, which stinks. And you guys are starting to get the hang of this. I'm sure you're aware. The more cases we have, the more people are going to be in the hospital. The more people are going to need more direct care. And the more people are going to die per day. So be smart, be safe, take care of yourself, take care of your loved ones. Protect yourselves. Wash your hands, social distance, wear a mask out in public. Try to prevent. Work on the basic hygiene stuff to prevent you from maybe getting this. It's not all hygiene, but if you do that, it's going to help a little bit. All right, so there's a COVID update. This number, I don't know why they keep putting it up here because that is definitely contradicting to other numbers, percentages that they put up there. Last I knew, our percentage was like 11.7 range, 7.7. Herkimer County, which is our neighboring county, they're at like 13%. So that's like of all the testings that are given, all the tests are given, that's how many would be diagnosed with COVID. For that number, I don't think that's valid. But be smart, be safe, be awesome. Don't get COVID. All right, daily agenda for today. Here we go. Let's check out where we're at. We're at the best class today, you know that. But welcome back. Our quote of the week comes from Dr. Seuss. Sometimes you'll never know the value of the moment until it becomes a memory. This moment that you're sitting here, this virtual learning, you may think it stinks, you may hate it, you may hate coming on to class, you may love it, being in your jammies, your comfies, and just logging on in. If you wake up in the morning, brush your teeth, do all that stuff. But this will soon be a memory that you'll definitely never forget. So let's just embrace it. All right, daily agenda for Monday, January 11th, 2021. This is day 4. We're going through chemical bonding still. We finished up with ionic bonding. We are going through part 2, which is covalent bonding. We started talking about covalent bonding. We will start off with midterm review, which this is going to be on the atom. We'll do review for the midterm from now until the midterm. There's 3 total Regents chemistry teachers at Proctor. There's a AP chemistry teacher, and there's a non-Regents chemistry teacher at Proctor. So you have 5 total chemistry teachers at Proctor. The 3 chemistry teachers, the other 2 chemistry teachers, they want to push the midterm back a little bit. We would have been okay, but the midterm, just so you guys know, it's going to be either the Tuesday, January 26th, or the 27th, depending on which day it falls in, if we have class or not. So the 26th or 27th, I'll start putting that up on my stream so you guys could get aware of that. But you still have a couple of weeks to start preparing. And my warm-ups going on forward are all going to be midterm reviews. So you can anticipate that midterm review from Unit 1 through Unit number 5. Everything from Unit 1 through Unit number 5 is going to be detailed on the midterm. So I can't tell you what to study. I would study Unit 1 through Unit 5. If you can handle these midterm reviews, this will help you too. All I have left to finish up for the midterm review or midterm content for the midterm is this unit right here. So if we're like so far ahead, we get done with this unit this week. I'm not going to review all next week. We'll just start the next unit just to get ourselves a little further ahead of the game. So midterm review, your midterm is going to be January 26th or 27th. Just start reviewing some exit passes. You can check out your notes. You get bored at home, no work to do. You could always review your notes from Unit 1 through Unit number 5, see what you did. And then hopefully those make connections to what we did in the past. All right, after that midterm review today, we're going to go through a YouTube video, probably today. And then we'll go through some guided notes, and exit pass probably won't be assigned till actually one more class. The attachments are below. We have a reference table and a calculator. We're going to start for the midterm review. So the midterm review, the date is not accurate, but it's going to be the one right above. So 1/8/21. Please click on that one right there, 1/8/21. A couple of you guys emailed me about warm-ups or maybe the examples on types of bonds or balancing reactions, the examples of not having the answers. So the warm-ups and the examples that I do in class, you don't even have to worry about submitting them right now. I will definitely let you know if there's something that I'm going to grade that you're going to submit. Then I will let you know. But right now, the warm-ups or the examples are not going to be graded by myself, nor will they hurt you for your quarter grade, your overall average. The exit passes are what I grade. So if there's something that's like missing answers on the exit passes, then I appreciate if you let me know on that one. The warm-ups or the examples I just throw up there because I usually go up over them as well. Those I will not grade. But I'm really trying to be cautious on my exit passes to make sure that they all have answers. All right, so here we go. Please open up the warm-up. It's 1/8/21 review, and it's on the atom. I think there's 10 questions possibly. 10 questions there. 10 questions. So 10 questions on the atom. If you want to pull out your notes, I guess this is a cool thing about being in the virtual world. You could pull out your notes go to Drive. You all could do this. Your notes should save automatically. If you go to your Drive, hopefully you guys know what the Drive is. So this is where the Google Docs can be stored on your end. If you go to your Drive, you search probably Unit number 3, the Atom Guide Notes. You should be able to find your notes for the class. Unit 3, period 6, 7. So you can use this to help you out with the examples if you want to. You don't have to. But before I give you time to work on this, a little snapshot of where we were for the atom. We talked about the history of the atom. We talked about subatomic particles, ions, isotopes, mass, electron configuration, and the ground state versus the excited state. I'm not going to go through this whole thing again. You could check it out, but when I go over the examples or the answers, I'll probably pull back a lot of this information. So hopefully this will refresh what we talked about with the atom. All right, since there's 10 questions, I'll only give you 10 minutes. I think 10 minutes is enough. So I'll give you 10 minutes to work on this. At 12:04, we will review this. So please work on this from now till 12:04. Now to 12:04, please work on it. Warm up. Thank you. Okay, I hope you had enough time to go through these questions. I hope you actually attempted these questions as well. One of my quotes I say all the time is, whatever you put in something is what you get out of it. If you just go through these 10 minutes and just wait for me to get back on, then you don't do it, then you're probably not getting much out of it. If you go through it, try it out, you'll probably get more out of it, obviously, than not doing it. Just like logging into class. If you're paying attention today or every day, then you'll get something out of it. That goes a long way in life. Not just this class, any class. You get a relationship, then you don't put anything into your relationship, then you're not going to get anything out of it. So here we go. Whatever you put in something is what you get out of it. Question number 1 says the atomic number of an atom is always equal to the total number of what? Please put your answer in the chat. Best answer for question number 1, please. Thanks, Tintin, Michael, Adina, thank you. Thanks, Zin. Asim, thank you. Emma, thank you. Thanks, Kai. Kim. All right, did get a few different answers. Thank you for submitting them, everybody. I did get a few answers here. The atomic number is going to be the same thing as the proton number. So I did highlight over here to the left in the notes. Atomic number, probably forgot it. I'm assuming you guys know this. Atomic number is the same thing as the proton number. That is it. Atomic number equals the proton number in the nucleus. Choice B is definitely the best answer. Some C's and some D's for answers. Neutrons and protons are going to be the mass. So choice C would have been the mass. And choice D, nothing at all. Protons plus electrons, no. So atomic number is the same thing as proton number. Definitely need to be aware of number 1. Atomic number equals a proton number. They like asking, starting off the regions like that. Question number 2, let's try this one out. The atomic number of an alkali metal. All right, talking about atomic number, talking about alkali metals is what? Please put the answer in the chat. Thanks, Faith. Nadia, Alex, thank you. Thanks, Irvin. Emma, thanks. Kai, Joseph, Mike. Wow, seems like you guys got that one right. Most of you. All right, so this is like a periodic table question. Here's my awesome periodic table. You know a lot more about this periodic table now than beginning of the year. So breaking up this periodic table, let's figure out some things here. Let me highlight some stuff here. This is group number 1. That is called alkali metals. They have 1 valence electron. They have a charge of +1. They bond typically at group number 17 when they bond. They have, I already talked about 1 valence electron. They're the most active metals. Group number 2 are called alkaline earth metals. They have 2 valence electrons, hence 2. They have a charge of +2, so they want to lose 2 valence electrons. It's the second most reactive metals. They're all solids at STP, standard temperature, standard pressure. Next up, this big chunk, this big group in the middle are called transition metals. Transition metals are called colorful ions. Their number of valence electrons, they vary. There's 2, there's 3, there's 1 valence electron in this. They form alloys, and these can be found alone in nature. Most elements are solids at STP. The only exception is mercury, which is a liquid at STP. Next main group you should be aware of are called halogens. Halogens have 7 valence electrons. 7. They have a -1 charge, so when they bond, they're going to take an electron very easily. You have all 3 phases of matter. You have the gases upstairs. You have a bromine is a liquid, and solids are below. So halogens, they combine with group number 1. Last group to the right is called inert or noble gases. Inert or noble gases. Group number 18, they're stable octets. The only exception there is going to be He, which is it's a stable, but there's not 8 electrons. There's only 2 electrons in the first ring. They're all gases at STP. The last main element is the most reactive element. It's hydrogen. It's a group of its own. It's a nonmetal, 1 valence electron. It bonds with a lot of elements. So you should know the main groups of the periodic table. You should know how they're organized, classified, the basic properties of them as well. Might as well go through the metalloids. Metalloids on the staircase, they divide metals and nonmetals. Here's my first 4. They're on the staircase. The 5th one is below. 6 works its way back on up. Those are the metalloids. They have properties that are similar to metals and nonmetals, depending on their pressure and their temperature. Metals, just going crazy on this again. Metals are to the left of the staircase. They're malleable, ductile. They're good conductors of heat and electricity. They shine when light hits it. To the right of it are nonmetals. So nonmetals to the right. But we talked about that. We'll pull that back up. We'll probably we will do a review for periodic tables, so we'll go through that. This question was asking about alkali metals. I think a lot of you guys already put the answer for it. Alkali metals, talking about group number 1. This is alkali metals. H is not alkali metal. So H is not alkali metal. That's in a group of its own. They want to know atomic number. Atomic number for alkali metal. Talking about that 3, 11, 19, 37, 55, or 87. Any one of those would have been the right answer. Let's check it out. Put an arrow still. Yeah, 11 would have been a solid answer for number 2. Choice B, a lot of you guys put that. You know alkali metals, you know where they are, cool. Number 3, an atom of Ra226 contains what? Please put the answer in the chat. Ra226. Awesome. So I have a lot of A's and I have a couple B's for the answer. So let's refresh on this one. This is standard notation. In standard notation, you have the number upstairs represents my atomic mass. So that top number is mass. The number on the bottom is going to be proton number. So mass upstairs. And the number on the bottom is going to be atomic number. So number on the bottom, proton number, atomic number. So we should know that. So a lot of you guys put A. There are 88 protons, definitely. 88 protons. And neutrons, 138. It looks like a decent number. Some B's I had here. 88 protons are like. The electrons are the exact same as protons in an atom. This is an atom. Why? Because there's no charge at the top right. If there's a positive or negative up there, then it's an ion. So if it's at 88 protons, 88 electrons, that would be a good answer. There's not going to be 138 electrons. That's cray. 88 electrons, that's good. Neutrons, talk about in a second. 88 electrons is good. No, we know there's going to be 88 protons. So it's definitely not going to be a couple of these. Definitely not going to be choice D. Definitely not going to be B. So neutrons, how do you find neutrons? Neutrons are calculated by taking the mass minus the proton number. So subtract those two numbers in standard notation, then you can figure out the number of neutrons. So again, neutrons, subtract 226 minus 88. You would discover that choice A is the best answer. So it's definitely not going to be 226 neutrons. That's the mass. No, that's not right. So choice A is the best one for number 3. A lot of you guys picked that one as well. Number 4, I talked about this the other day. Number 4, talking about Rutherford, I was confused, and that sparked my idea of doing like this review. That's why we're doing it. All right, after bombarded gold foil sheets with alpha particles, scientists concluded that the atom contains, best answer please, put it in the chat. Okay, I don't have to redraw my drawing again, I don't think. Yeah, so it should have been an empty space. That's an atom to the left, we should know. The left, that maroon is going to represent the nucleus. And inside the nucleus is going to be my protons plus my neutrons. So nucleus, and inside of that is going to be my protons, which are positive, plus your neutrons, which are neutral. Protons, neutrons, inside the nucleus. Orbiting around are my electrons, buzzing around different shells, rings, energy levels. So choice B is the best one. Atom is most empty space with a solid, dense, positive core. Rutherford said that. Number 5, in which pair of atoms do the nuclei contain the same number of neutrons? Please put the answer in the chat. Same number of neutrons. Take your calculator out, some simple math there, hopefully. Same number of neutrons. So for each situation, in case you're stuck on this, I would subtract these two numbers, 7 minus 3. Subtract 9 minus 4. If it equals the same number, it's the same number of neutrons. So it's not going to be choice A. No. Choice B, you have 40 minus 19 and 40 minus 17. Those numbers are not the same. Therefore, neutrons aren't the same. So neutrons, no, not the same answer. Choice C, to take 40 minus 20, 20. 40 minus 20 is 20. 38 minus 20, 18. 38 minus 18 is equal to 20. Therefore, you have 20 neutrons in both. That looks like a solid answer. Choice D, not the same number, not the right answer. 5, best answer is choice C. 5 is C. Next up, number 6. When electrons of an excited atom fall back down to lower energy levels, there's a emission of energy that produces what? Please put in the chat. Yes, Faith, that's C. Alpha particles, you're rolling a C right now for Rutherford. Yes, John. Yes, Mike. Jimmy La, yep. We didn't talk about gamma yet. Yes, Joseph. Kaya, Alex, good. Spectral lines. Best answer for this one, spectral lines. We talked about this when we talked about excited electrons. When I was in school, I did the flame test. Remember I did that colorful little demonstration in front of us? And then the reason why I did it, because they gave off different colors, but as you analyze them through a spectroscope, they gave off different spectral lines, the spectrum. Question asks when it goes from falls back down to a lower energy level, what happens? Bright line spectrum is produced. So spectral lines, choice C is the best answer for that one. You can see in the notes as well. Number 7, atoms of every isotope of calcium atom have what? Best answer, please put in the chat. Every calcium atom has the same number. Yes, Faith. Yes, Tintin. Yes, Emma. Check that one out again, Kai. Yes, Michael. Jumila, check that out again. Atomic something. Masses could be different. Yes, Urban. Then good. So atomic number. Choice B is the best answer. Atomic number is what's used to identify. It's like your social security number. 6 was C. 6 was C. Atomic number is the same thing as like the proton number. It's like your social security number. It's used to identify it. Atomic number, every calcium has the same number of protons. So every calcium Ca is going to have 20 protons, 20 atomic number. The masses can change. If you remember, the masses come from all the average isotopes. It's a mass of all the average naturally occurring isotopes. So that is choice B for number 7. Number 8, which pair represents the same element? Must represent atoms of the same element. Please put in the chat. Yes, Kai. Alex, good. Tintin, good. 3 for 3, 4 for 4, 5 for 5, 6 for 6, 7, 8. Nice. 9 for 9. 10 for 10. Wow. 10 for 10. Not bad. We want to break the streak. 10 for 10. 10 for 10. Looks like we are. The answer is B. Best answer is B. Proton number identifies the element. Nice job with that one. Everybody got that right if you submitted the answer. Number 9. Let's take some time to do this one. A sample of X contains 90% of X30 atoms, 8% of X37, and 2% of X38. The average isotope mass is closest to what? Please put in the chat. All right, thank you for submitting it. Looks like several same answers. That's good. Always good to see that usually. To calculate atomic mass, all you have to do is, this is a note packet that you guys completed. Atomic mass is the weighted average of an element's naturally occurring isotopes. How do you calculate it, or where does it come from? It's the percent abundance of the isotope as a decimal times the mass plus percent as a decimal times the mass plus percent as a decimal times the mass. In class, we analyzed several examples, and it looked kind of something similar to this. I copy this. It's probably not going to work out too well. Let's see if it works. I don't think it's going to paste into annotate, but we'll try it. No, didn't think so. All right, but that's what we're going to be using to calculate this. In case you're stuck on this, let's go through this one. I know there's some students that are lost with this. How did you get that answer? Where did it come from? This is where it came from. So it's going to be percent as a decimal times the mass plus the second one. So percent as a second isotope times mass plus a percentage as a decimal times your mass. That's the calculation. It is nowhere on the reference table. So this is something you're just going to have to kind of memorize in the event, which they probably will give you on the Regents somewhere if that time comes. So the first one up, so to change a percentage to a decimal, what do you have to do? You have to divide by 100. So how do you divide by 100 for the first one? 90%. My original decimal is at the end. Boom. Convert that percent to decimal. Let's move the decimal over 1, 2 humps over to the left. So 0.90. So 0.90. The mass is going to be 35. The next one is going to be 8%. Convert the decimal. 1, 2. Convert that decimal on over. So it's going to be 0.08. Wow, I've really grown with my mouse and my Zoom screen drawing. Mass is 37. Plus the last one, percent as a decimal. 1, 2 spots over to the left, you have 0.02 times a mass of 38. So multiply all those together. Yes. So multiply all those together. 0.9 times 35 plus 0.8 times 37 plus 0.02 times 38. It looks like a lot of people got choice B for the answer. So throw in your calculator. Hopefully you get that right. Hopefully that helped. If you requested me to go over it, hopefully that helped. If you have any questions, you could privately message me. I won't call you out. I'm just going to make sure it's the right answer too. I'm sure it is, since the majority of the population got it. Yeah, 35.22 would be a solid answer. But 35 is a good answer as well. Any other questions? Okay, moving on forward. A couple more questions. Our last question. Next one up, number 10. The elements of the periodic table are arranged in order of increasing what? Please put in the chat. Joseph said A. A is the right answer. Joseph said A. A is the right answer. Atomic number. Perfect. Atomic number. Modern periodic table is arranged by increasing atomic number. Sorry to cut everybody else off. I know you guys know the answer. Atomic number is how the modern periodic table is arranged. And we'll talk about the periodic table for a different review. All right, that concludes the review, the warm-up for today. Close that out. Good to go. You don't have to submit it. I'm not grading it. We went through it. Not grading it. All right, moving on forward. Next on up is going to be what are covalent bonds. So I'll play a flick here, and then we'll get right to the notes.
This video we're going to talk about some special covalent bonds. We'll start here with molecular oxygen. Molecular oxygen is found as a diatomic element, so it has two oxygen atoms bonded to itself. And we want to see the structural formula for oxygen here. So the first thing we'll do is draw a Lewis structure for each one of these oxygens. If we look on the periodic table, oxygen is here in group 6, and so it has 6 valence electrons. So we can put those 6 valence electrons around each oxygen. Now, almost all atoms want to follow the octet rule, which states that an element is going to try to have 8 valence electrons. So these oxygen atoms are going to pair up and share their unpaired electrons. Electrons always want to be in a pair. So these two at the top are going to be paired up. And then the only other option here is that oxygen is going to pair up the ones at the bottom as well. If they do that, then each oxygen is going to view its own electrons as its electrons, and then it'll also view the ones that it's sharing as additional electrons. And so each oxygen now has 8 valence electrons. Let's rewrite this as a structural formula, redraw it here, and we can put this what we call a double bond between the two oxygens. And so this is our first special type of covalent bond. It's a double bond. And so some elements may share more than just one electron in a bond. Okay, here's our next example, molecular nitrogen. It's also found diatomic, so 2 nitrogen elements bonded together. If we look at the periodic table, we can see that nitrogen is over here in group 5, and so it has 5 valence electrons. So let's put those around each of the nitrogens. And then we can start pairing up the unpaired electrons. So we'll pair up these 2 at the top, pair up these 2 at the bottom, and then we can also pair up these 2 in the middle. And so nitrogen is actually going to form what we call a triple bond. And so sometimes elements will even share 3 electrons in a bond. Now the maximum amount of bonds to have is really a triple bond. You don't have a quadruple bond ever happening. Now a triple bond is actually a lot stronger than a double bond, which is even stronger than a single bond. It's almost like if you've ever had a string, and if you have that string on its own and you pull it hard enough, you could probably break it. If you were to fold that string over and grab onto both ends now, it would be a little bit stronger. And if you could even fold that again and triple it up, it'd be even stronger so. And as you could probably see here, it would also get shorter. So a single bond is actually the longest bond, a double bond is a little bit shorter, and then a triple bond is the shortest of all the bonds. It's the strongest, but it's also the shortest. And that's 2 special covalent bonds, double and triple bonds.
Good grade.
All right, so single, double, and triple bonds we'll be talking about today. So please open up your guided notes. Forgot where we left off in the note packet. We're on, obviously, part 2 now, which is covalent bonding. But before we talk about covalent bond, we talked about ionic bond. With ionic bonds, we talked about a metal and a nonmetal. For example, like an Na and like a Cl bonded together. Na and a Cl. Na and a big Cl. This little example, just talk about. Na is a metal, Cl is a nonmetal. So those two things would bond together. It's a metal and a non-metal. We know that Na has a charge of +1. We know Cl has a charge of -1. We also know that in NaCl there was one valence electron from the Na. Just doing a little drawing session here. One little valence electron that was transferred on over to Cl. So it transferred the electrons. We should know that the Cl would have a bracket around it, 8 dots. You know the Na has brackets around that with no dots. It transferred its electron. Now we're talking about two nonmetals, like nonmetals bonded together. So two nonmetals bond together. We'll take a Cl and another Cl. Try to make them the same size, same level, but it didn't work out. So Cl bonded with a Cl. If you check on the reference table, you look at Cl, you'll notice that Cl has 7 valence electrons. I'll draw electrons here. So Cl has 7 valence electrons, again, just like it did last time. So we have 1, you can't see, try it again. 1, 2, 3, 4, 5, 6, 7. This Cl has 7 as well. And then when they bond together, what's going to happen? They're going to be sharing electrons, which are going to be, they're pretty tight. They're going to be close together in the situation. So those two are going to share those electrons. So those two are a lot closer than an ionic bond would be. So they're sharing electrons. They're kind of like locked in close together, and they're sharing them together as well. So two nonmetals, hopefully you can see the difference between ionic and covalent. So again, this is my ionic. It's a metal and nonmetal. This is my covalent, sharing electrons. But we'll talk about covalent now. Let's go through some of our notes. Hopefully I gave you enough time to find out where we left off. Here we go. Covalent bonds, topic number 9 we talked about. We talked about two nonmetals. They share electrons. They become each other. Their bond's stronger than ionic bond. Why? Because like they're sharing that electron. They're closer. If you and your boo are sharing your spaghetti, you're going to be closer. If you transfer it, you're not that close. You wash your hands, say, that's yours. I don't want it. Your germs. Don't share germs. So they're going to be closer for covalent bonds. Covalent bonds, there's no metal to conduct electricity. They cannot be broken down by dissolving or melting. We'll talk about this more in the next couple of classes. The electronegativity is less than 1.7. We talked about examples there. Now today we're talking about nonpolar covalent. So two types of covalent bonds. There's something called polar and there's something called nonpolar. So I'm not really sure. I don't think I did talk about this example, but the nonpolar covalent bond is going to be formed between nonmetal atoms. Let's just start writing some notes down now. I'll do another drawing session here, art class. So nonmetals nonmetal atoms with electronegativity from 0 to 0.3. And that we're going to talk about. If you remember electronegativity is going to be the attraction for electrons. The highest electronegativity was fluorine. Maybe you remember that. The lowest was Fr. So F really wanted to take electrons in really, really easily. Why? Because it was on the second ring and it had 7 valence electrons. It only needed one more. So the range here for nonpolar bonds is going to be from 0 to 0.3. When you subtract the two values, it's 0 to 0.3. In this situation, electrons are being shared equally Electrons are shared evenly or equally. Oh, electrons are shared equally. For examples, if I have two Brs or two Os, if I have diatomic molecules in the situation, Br2, O2, F2, N2, H2, there's a few examples. There's more. These would be sharing electrons equally. If something is a diatomic molecule, di is referring to two. To what? Two atoms, diatomic. Two of the same atoms that are bonding together. So diatomic means two of the same atoms bonding together. They would create a non-polar covalent bond. So ionic bond, there's only one type of ionic bond. Metal, non-metal. That was it. Covalent bonds, you could have non-polar, or eventually you'll see polar, which is going to be next time, polar covalent bonds as well. So how do I differentiate between polar and non-polar? One more thing to add up in our notes. Non-polar, I would just say non-polar means no pole. What does that mean? They're sharing electrons evenly. Non-polar means no pole. So non-polar, think of there's no pole for electrons. They're sharing them evenly. So I can't recall if I did give this example. If I did, I apologize. I'm going to draw something quick up here. I'm going to draw some people playing tug of war. You and your twin playing tug of war. So there's you, and there's your twin. You are playing tug of war. You and your twin, very similar personalities. You guys both work out. You're both just as strong as each other. There's you. You look alike. You act alike. Same mass. Very similar. So there's you. Oh, darn it. Arm's a little longer. And they're playing tug of war versus each other, so they're not going to be very happy. I'm going to put a nice little angry face on here. And it's get a little crazy. All right, so they are playing tug of war. Put a rope in between. And if you ever played tug of war before, the goal of playing tug of war is to try to take the other person and make them cross that ribbon. And then what's going to happen? They're going to fall into like a big, nasty mud pit. So I've made mud pit. All right, so in this situation, I have twin number one who's pulling to the left. Let's just put a couple other things in here too. Did I give you this example before? No, I hope not. I don't think I would have, but maybe I did. Situation to the left, let's say this person has a mass of 180 pounds. Twin number right has a mass of 180 pounds. Twin number one to the left is pulling with a force, we'll say a force of 100 newtons. So from the rope, they pull with a force of 100 newtons. Force is a push or pull. So force equals 100 newtons. The participant to the right, twin number two, is pulling with a force of 100 newtons in the opposite direction. So force equals 100 newtons in the opposite direction. So if they're both pulling in opposite directions, that rope is going to be pretty taut. There's going to be not much flexibility in that rope, and they're not going to move. They're both pulling with the same force in opposite directions. That rope not moving at all. So this would be like, in this situation, this would be like two different atoms. So maybe atom, say atom number 1. This would be atom number 2. Maybe they would be like a Cl. So two different chlorines. I have a chlorine here, and I have a chlorine here. They're both sharing that rope. They're sharing the electrons evenly. They're not moving. They're very close together. They're sharing them equally or evenly. Another thing to note is in this type of bond, if we cut them in half, it's the same thing on both sides. Like this female right here, same as the other one. They're similar, they're twins, but they're not the same, but they're a little different. Asim and Adina, different type of situation. Identical twins. I apologize. I forget what I'm dealing with sometimes in my class. So these are the same sex, the same way, all that stuff. Cut them in half. They're the same on both sides, and it's going to be nonpolar bond. So think of this example as we go through nonpolar bonds. Hopefully you guys somewhat understood that. It's one of my better diagrams I've made all year. All right, types of nonpolar covalent bonds. The first type of bond is going to be something called a single covalent bond. So we're going to draw some examples for a single bond, a double bond, and a triple bond. Some of you guys is going to take a couple different trials to understand. Some of you guys are going to get this from the get-go. So the first one's going to be a single covalent bond. What's going to happen here is we're going to do an example of Cl2. So I'm going to take a reference table handy. I'm just going to focus in on Cl. That's where we left off in our little diagram, my picture. I'm going to just take a little snapshot of that and probably get rid of it so I could refer to other things. So Cl, checking it out, we have Cl has 7 valence electrons. This first time that I'm going to do this, I'm just going to go through my mental state of how to make a Lewis dot diagram for Cl. I'm going to use Zoom Annotate, and then I'll put it on the drawing board as well. So I'll do it first, then we'll do it together, and then hopefully we'll paste it in here as well. The example I am going to use is going to be Cl2. So Cl2 is the first one. If they ever ask you to draw a Lewis dot diagram for Cl2, you would know that there's 2 Cls, one Cl with another Cl. So you don't have to copy this down yet. You would know that Cl has 7 valence electrons. So each one of these Cls has 7 valence electrons. The one to the left has 7, the one to the right has 7 as well. The one to the left, to make a stable octet, it needs 1 more electron. So 7, you need 1 more. That 1 more electron that you need has to come from the other Cl. So that 1 more electron you need, 7, 8, has to be smushed in the middle. So the first electron that I'm going to add is going to be smushed right in the middle. I know this Cl has 7 valence electrons, so I need 7 total dots around this. So 1, 2, 3, 4, 5, and only one's going to be in the middle. 6, 7. So there's 7 dots around that first Cl. Now I'm going to go to the second Cl, and that Cl has 7 valence electrons as well. It needs 1 more, 7, 8, to make a stable octet. That 1 more you need, smushed right in the middle. So 1 more you need has to go in the middle, and it still has 7 dots around it. When these two things bond, it creates something called a single covalent bond. What happens to a single covalent bond? It's going to share some electrons. Which electrons? The ones right in the middle. So that's going to create a stick. It's going to create a single covalent bond. And within that, you're going to have the sharing of electrons. So everything within this yellow circle is representing the sharing of electrons, or total number of electrons that are shared. Let's count them again. Let's make sure there's 8. 1, 2, 3, 4, 5, 6, 7. That's my original 7. That 8th one comes from the other Cl. So we're sharing that 1 Cl. Let's check out the other one. So let's check out everything inside of this light purple. Let's count them on together. That second Cl is going to have 7 electrons. 1, 2, 3, 4, 5, 6, 7. The 8th one came from that Cl. So that is going to be the single covalent bond that they're sharing. How many pairs of electron? A pair of pants has 2 different legs. A pair of electron has 2 electrons. So how many pairs? 1 pair. Total electrons. How many electrons are on that stick? 2 electrons. We'll do this again. So that's going to be a single covalent bond. Your Lewis dot diagram for Cl2 should look something, a lot of clicking here, something that's going to be similar to that. Cl2 should look like that. So we're going to draw that together. I'm going to go to Insert, Drawing, New. We're drawing Cl2, the single covalent bond, Cl, control, comma, 2. So we're drawing 2 chlorines. If you want to put this on a separate piece of paper and upload it, you can. So I'm going to make 1 Cl, make a kernel, a Lewis dot diagram for 1 Cl. My kernel for a Lewis dot diagram represents the protons, the neutrons, and the non-valence electrons. I'm going to blow it up a little bit. And around that Cl, you already saw, has 7 valence electrons. I'm not doing smiley face anymore. Sorry, guys. I'm going to make small little dots. That's what they should be. Once you have a small little dot, I want to insert shapes. So shape, and then just a circle. You can put a smiley face. It's fine. So a circle, once you have one of them, I'm going to copy, hit Control-C, and paste it 6 more times. I need 7 total. 1, 2, 3, 4. Sorry, counting out loud. So starting off, I'd make a Cl with 7 dots around it. I really don't care where the electrons go on the first one. 1 to the north, 1 to the east, south, west. Follow that sequence, that's fine. So nonpolar bonds are 2 of the same elements, typically, bonding together. Diatomic are 2 of the same elements bonded together. So there's my first Cl. You could do a Lewis dot diagram for chlorine. It would look similar to that, I'm sure. Okay, once you have that, I'm going to highlight that chlorine. I'm not going to make this all over again. I'm just going to copy and paste it. So if I have a Chromebook, I'm just going to click on it, drag it, click on it, drag it, click on it, drag it. So you have that box, so you can highlight it. Should be a blue box around it. I'm going to hit Control-C, copy, and hit Control-V, paste. Don't click off it with your mouse or your keypad. Just scroll on over to the right or the left. I don't care. I'm going to go to the left, I guess. So what's going to happen here, this has 7 valence electrons. It needs 1 more. It's going to have to get from the one to the right. So I have to shift around one of these electrons. Just going to pull it all over to match up to the left. Cl and Cl. What happens here, the last thing I need, and I'll give you guys some time, is I'm going to add a stick in between them. This is the toughest part. I don't know why. So connecting these 2 things with a stick or a line. So connect the 2 electrons. The stick. Cl2 should look something similar to that. Once you have that image, you can save it and close it. Again, I'm just going to talk myself through this again. Give you guys more time to do this as well. So if you have 2 chlorines, Cl2, if they ask to draw a Lewis dot diagram for Cl2, I have 2 chlorines. This chlorine to the left is going to have 7 dots. 1, 2, 3, 4, 5. 6, 7. It needs one more, so that one more you need has to go in the middle. The chlorine to the right has 7 dots. It needs one more, so that one more you need has to go in the middle. And this is going to be connected with a single covalent bond. Single covalent bond connects both of those. Drawing this thing on up, if you're doing Cl2 with bonds and sticks, the green sphere represents chlorine. If you have a ball and stick kit home because someone awesome gave you one for the holiday, then you could do this. But Cl represents chlorine, it's green. If you look at this, there's only one open hole for an electron. So that's an atom. There's one more hole. That means that's many more bonds it could potentially have. Chlorine has 7. There's one more hole for something else. Here's another chlorine with one hole. What happens here? This creates a single covalent bond. Single covalent bond right there. All the holes are filled. That's a stable octet. They are sharing one pair or 2 electrons. Save it. Close it when you're done. Gotcha. Gotcha. If you have to refresh, go for it and scroll down to like page 24. Does anybody need more time talking about CL or drawing the CL2? Hopefully I'll get through one more example today. Yeah, I'll definitely get through one more. Maybe we'll get through 2. I'm not sure. All right, so Cl2 looks like that. It's a single covalent bond. Looks like we're good with that one. How many pairs of electrons are shared? Pairs of electron, pairs can be one pair right there. Those are the shared electrons. So one pair, total number of electrons, there's 2 electrons on that stick. So again, one pair and 2 total electrons. They love asking that question. All right, next example is going to be a double covalent bond. The example I'm going to give you is going to be O2. So here we go. I'm going to talk myself through this one again. I'm going to focus on oxygen. Oxygen has 6 valence electrons. So let's talk about O. For O2, so some of you guys could probably visualize this and start thinking about what's going to happen here. So my example is O2. It's oxygen gas. In oxygen gas, you have 2 O's. You have an O and an O, obviously. I have an oxygen and I have another oxygen. Each oxygen has 6 dots. So let's focus on the one to the left. It has 6 dots and then 6 valence electrons, and it needs 7, 8. So 6 electrons, it needs 7, 8. It needs 2 more electrons. Where is that guy going to get them from? It's got to get them from the one on the right. So if it has 6 dots, you need 7, 8. The 2 more electrons you need have to be smushed in the middle. So it has 6, 7, 8. 2 more that you need go right in the middle. So start off with the 2 that you need. 1, 1, 2, and then there's still 4 more around it to make 6. I don't care where the rest go, but it still has to equal 6. So 2, 3, 4, 5, 6. There's my 6 electrons. The oxygen to the right has 6 dots. You need 7, 8. The 2 more you need, 7, 8, have to go in the middle. So 1, 2 in the middle, has to go in the middle. And then I don't really care where the remaining 4 go. What happens here? We have a double covalent bond created. It's connecting both of these. So here to here, here to here. It's a little extended, but it's okay. And this would create a stable octet. So a Lewis dot diagram should look very similar to that in the example. Let's count them on up. Let's see if it works out here. So that first oxygen to the left, just be sharing those electrons right there. Let's count them on up, see what happens here. So count them up. We have 1, 2, 3, 4, 5, 6 original ones. And it's sharing 7, 8. Okay, that's a stable octet. That one's good to go. Let's check out the one to the right. 1, 2, 3, 4, 5, 6. Then sharing those two right there, 7, 8. So these electrons right here in the middle are the ones that are being shared. How many pairs? 1, 2. How many total? 1, 2, 3, 4 electrons on that. So let's draw this one up. Oxygen gas, O2. So this is the last one I can do today. I'm not gonna rush to the last one. So click on double covalent bond, click on it, go to insert, drawing, new. And we're gonna draw a hotspot from school, and it says I have a new text message. Never saw that before. Cool. All right, so anyways, for O2, I'm going to start off with the text box. I'll just say I'm going to draw O2, which is oxygen gas. So diatomic molecules that are bonded together, like O2, Cl2, N2, it's going to be that element, then gas. So O2 is oxygen gas, Cl2 is chlorine gas, N2 nitrogen gas. So that's another heads up for the future. So the first one we're going to make is O. I'll make an oxygen. And the first thing I would start off with is making a Lewis dot diagram for O. Again, I'm going to take my shapes and make a circle, small little circle for electron. I know there's going to be 6 total electrons. So I'm going to make a circle, copy, and paste it 5 times. So my thought process, I'm making a Lewis dot diagram for this thing. There's 6 electrons. I need 2 more. So I don't even care where you put it. You can we'll start north. The first one doesn't really make a difference where you put them because you can put the other one on the opposite side. I'll just stick with my routine of making a Lewis dot diagram for O. Same sequence, same order. So that has 6 valence electrons. The second oxygen is going to have 6 as well. It's going to need 2 more. I'm going to copy this image, Control C, and paste it. I'm going to drag it on over to the right. And I'm going to readjust this a little bit here. So readjust it. My valence electrons, I didn't mean to move that O2 over. So readjust my valence electrons. This oxygen to the right is going to have 2 electrons in the middle again. So this is going to have to shift on over to the left. That would be a Lewis dot diagram for O2. We'll throw some little lines in between. Hopefully this connects. That would be a double covalent bond. Let's save and close. I'll be right back. Darn it. So that would be a Lewis dot diagram for O2. All these notes, crazy. I'll work with doing here. Just kidding, I love it. All right, so there's my O2. Oxygen gas, sharing 2 valence electrons. So in O2, what's gonna happen? You have oxygen, there's a sphere that represents oxygen. There's 2 empty slots for 2 more electrons. The second one's going to be the exact same thing as well. 2 twins fighting tug of war. This is going to be filled not with sticks this time, but instead it's going to be filled with springs. This is going to create a double covalent bond between the two atoms. That is O2. See here, there you go. O2. O2 atom. Boom. Sharing of two valence electrons, two pairs of electrons, four total electrons. It's a double covalent bond. You can save it and close that. Be aware of how to do that one as well. When we finish up, pairs of electrons shared, there's going to be two pairs and four total electrons. Next class, we'll talk about the triple covalent bond. It is N2, in case you want to try that one out on your own. It's N2, but we'll do that one next time in class. On that note, that's it for today. Hopefully you guys understand the difference between single and a double bond. We'll get to triple bond as well. But that's it. Have a great day. Make good decisions. Be kind to one another. And protect yourself. Don't get COVID. Bye, guys. Have a good day. See ya. Bye, Nadine. Bye, John.
Have a good day.
Bye, Faith. Bye, Kai. Bye, Michael. See you, Kim. Have a good one.